Now I will talk about how can we calculate the lateral resolution. So this is our spectral domain OCT setup, and we can take the image from here in the spectral domain setup. This is the laser source. We'll take the image here. So it is important to know what is the lateral resolution of the setup. So I'll talk about how can we calculate the lateral resolution. Let's go some basic. So lateral resolution depends on several things. So this is lateral resolution. It depends on the wavelength. Say for example, in our case, we wanna calculate the wavelength of. We can use the laser source with the wavelength of 800 nanometer, and F is the focal length of the objective, D is the spot size of the beam. So one thing that I want to talk about is that there is a relation between the lateral resolution and depth of focus. Actually, there is a trade-off between the lateral resolution and depth of focus. So if you want to have the higher depth, if you want depth is high, then lateral resolution will be low, and vice versa. That is, if depth is low, then we can have the higher lateral resolution. So here is the two objective, one with low NA, another with the high NA objective. And if you look at the depth, so D is the indicator of depth. So for the low NA objective, we can have the higher depth, but the lateral resolution will be low, because if D is low here in this equation, then the del X will be low too. If we use the high NA objective like this, then we'll have the low B. If B is low, then we'll have the X value, del X will be also low. So for the application, we have to decide that from the design point of view, we have to decide that how much lateral resolution we want and how much depth we want. Based on that, we have to select the numerical aperture of the objective, and we have to choose like that way. So now, for example, we have selected the setup, we have designed the setup. Now we want to calculate what is the lateral resolution. So how can we do that? Say this is our setup, and if we want to calculate the lateral resolution, we have to use a target. Say we can use in the sample arm, we can use the USF 1951, like this kind of target. And you can see that this is basically nothing but black and white strip. That means we will take some cross-sectional data of the USF 1951, and from this data we will try to figure out what is the lateral resolution of our setup. Say here is one of the cross-sectional images of the USF 1951, and we can see that when there is a black strip, where the intensity is high, when there is a transparent thing, the intensity is low. In x-axis is in dB, y-axis is in dB, and x-axis is in micron, the actual length. So this data is taken by averaging few depth profile. We did the averaging because we wanna reduce the noise. If you do the averaging, the noise will be reduced, because noise have both the positive ints and negative ints. So overall they will be reduced. So now in the next step, what we need to do is we have to subtract from say one point minus another point. That is if this is a vector, then we have to subtract along the x-axis, say like say b 1 to in minus 1 minus say b factor 2 to in minus 2, something like that. Then we will find the sharp edge, how sharp the edge is. Basically, if we zoom this this graph. Or before that, all you can do is we can make like everything in like positive. You can take just absolute value of these data, absolute value of this data, and if you take the absolute value of this data, we'll find all the positive peak here. So all the positive peak. If you zoom in one of the peak, so this is one of the peak. So similar way we can calculate. Similar way means the way we calculated the axial resolution, we can do the similar way here. That is, we have to figure out what is the peak. So this is peak. Peak is, say for example, here is say 75 dB, for example, and the minus 3 dB point will be say something like here. So that is say 72 or whatever dB, like say for example 72 dB. So we need to know what is the physical distance from here to here. If we look at here and look at here, what is the distance between these 2 points? So say for example this one is say like 20 micron, for example. If this is 20 micron, that means our lateral resolution is 20 microns. What does that mean? That means is that we will be able to differentiate anything greater than 20 microns. If anything less than 20 microns, or the like spot size or something, some texture is less than 20 microns, will not be able to distinguish. So in this way we will be able to determine what is the lateral resolution. So this is the MATLAB code. So you have taken some data and so select some area. So we don't need to select all the area. Say if it is the, say for example this is like yourself target, so select some area. Say we are selecting say this area, for example, and then take the difference. So take the difference between these two, then you can do like all other steps. For example, you can use all these steps and move forward, and finally you will find the lateral resolution. Whatever value you will find, that is the lateral resolution of that system. So in this way we will be able to determine the lateral resolution of either 800 setup or either 1300 setup. So one thing that's to remember is that during the system design we have to think about like what is our priority. Do you want to have the higher depth, or we want to have the lower depth? If you want a high depth, like if you want to take the image in higher depth, so 2 millimeter or 3 millimeter or whatever, that means our lateral resolution will be low. If you want to image say a small depth of area by increasing the numerical aperture of the objective, then we will be able to take the image, then our depth of image will be low. So thanks.